I'm just going to prove a little identity about conics that you need to know, and that is that PS plus PS dash is equal to 2a. Now this proof, I'll use it with the ellipse, and I want you to have a go at it afterwards yourself using it for the hyperbola. It's a pretty simple proof, and what it's based on is that PS over PM is equal to E. So it's using the focus directrix definition of a conic. And what we're trying to prove is that this distance plus this distance is twice the distance out here, is equal to twice A. And so this statement tells me that PS must equal EPM. Similarly, that by the symmetry of the ellipse, PS dash must equal EPM dash. So if I add PS plus PS dash, I get EPM plus PM dash. Now looking at PM, this distance here, PM dash, this distance out here, if I add them together, I'm getting the total distance between the directrices. And that total distance is 2 times, and the directrix, remember, is x equals A over E. So it's 2 times A over E. So what I've got here is I've got equals E times 2A on E. E's cancel, simply equals 2A. So PS plus PS dash is equal to 2A. End of proof. Okay, here's a neat little HSC question that makes use of this property. This came from 2006 HSC, question 2, part D, and it makes use of the PS plus PS dash equals 2A property. So it says the equation of this modulus plus this modulus equals 10 corresponds to an ellipse in the Argand diagram. Write down the complex number corresponding to the centre of the ellipse. So if we have a look at what we've got up here, when we talk about the modulus of z minus 1 minus 3i plus the modulus of z minus 9 minus 3i equals 10. I'm going to make that the modulus of z minus 1 plus 3i plus the modulus of z minus 9 plus 3i equals 10. Now you've got to remember what this statement is saying is that this is the distance that z is away from the point 1 plus 3i. So if I want to plot that, I'd have to plot the point 1, 3. And this is the distance that z is away from the point 9 plus 3i. So I'd plot the point 9, 3. And there they are. And so it's saying that the distance that z, so I'll put a complex number z up, is away from here, plus the distance z is away from here is equal to 10. And so this is fitting nicely into our ellipse definition, and we're starting an ellipse like this. Oops. Well, maybe not like this, but you get the idea. An ellipse. And what we can do now is we can say that the first question asks, write down the complex number corresponding to the centre of the ellipse. It must be the complex number in between here. So it must be this number right in the centre at 5, 3i. So for part 1, I can say the centre is in the middle of those focus. It's 5 plus 3i. Okay. Sketchy ellipse. Dodgy. Let's take the lengths of the major and minor axis. Well, what we've got here is this PS plus PS dash is equal to 2a. And so 2a must equal 10. So I can state straight away that 2a is equal to 10, and that is the major axis of an ellipse. So that's this distance across here, that's the major axis. So the major axis runs from there to there, it's equal to 10. Now to find the minor axis is this length down here. Okay, I'll find the semi-minor axis first. So I know this length out here is going to be is 4 units. It's 4 units from 5 out to 9. And so that's AE because the focus is at S is at AE. So in other words, I know that AE is equal to 4. So I can use the formula to find B. B squared is equal to A squared 1 minus E squared. I'll have to expand that out. I'll get B is A squared minus a squared e squared. And so AE is 4, so a squared e squared is 16. And a squared, well, 2a is 10, so a is 5. A squared is 25. So b squared is equal to 9. And then b must be equal to 3. So 2b will be the length of the minor axis is equal to 6. That'll be the minor axis. 2b is equal to 6. Now with that information, I think I'll re-sketch my ellipse a lot neater, although it is still freehand. Okay, so I have over here at 5, 3 my centre. I have a focus at 1, 3 and a focus at 9, 3. I have the major axis is 5 units long, so it's going to go through here and through here. I have the semi-major axis the semi-minor axis is 3 units, so it's going to come down here and it's going to come up there. So I'm going to get an ellipse that looks more like this. Well, you get the idea anyway, without the bumps. And that's a little better representation of this ellipse. Okay. Last part of the question makes a nice little connection back to the values of the argument for complex number z corresponding to points on the ellipse. So z is all points on the ellipse, so z varies as it moves around. Z is all these points on the ellipse. Every single point on the ellipse is encompassed by z. We can see that z goes, the argument of z starts down here as 0. It increases up until a point of pi on 2. So for that third part of the ellipse, the argument of z, any point in the ellipse, must be less than or equal to pi on 2 and greater than or equal to 0.